So backward differences for a given sequence Pn, n is equal to 0 to infinite. It means this is an infinite sequence. The backward difference denoted by nabla Pn is defined by nabla Pn is equal to Pn minus 1 for all n greater than or equal to 1. So higher powers of nabla can be determined or defined recursively as nabla into nabla k minus 1. Okay, operating on Pn can be written as nabla k of Pn for all k greater than or equal to 2. So it means nabla is a linear operator and it can be operated over the function linearly. So Newton's backward difference interpolating polynomial using backward difference operator can be written in a new form. So if the interpolating nodes are reordered from last to first as xn, xn minus 1, so on x naught, then Newton's divided difference interpolating polynomial takes the form as given below. So Newton interpolating polynomial 5.14 so is written here. So this is Newton divided difference interpolating polynomial. So if we change this divided difference into forward difference, we obtain a Newton's forward difference interpolating polynomial. And if we change this divided differences into backward differences, we will obtain Newton's backward difference interpolating polynomial. So we came back to the backward difference interpolating polynomial. How we can write. So this is Newton's backward difference interpolating polynomial. So if the interpolating nodes are reordered from last to the initial or last to first as xn, xn minus 1, xn minus 2, xn minus 3, xn minus 4, and so on, x naught, then Newton's divided difference interpolating polynomial takes the form as given below. Pn of x is equal to the first zeroth divided difference and then plus first divided difference. So here we have changed the order. So in the forward difference or in divided difference, if you observe that here we write f of x 0, f of x naught, and then here f of x naught and f of x 1, or you can start with xi plus 1. But here xn and xn minus 1, so x minus xn then plus. So this is the second order divided difference, xn, n minus 1, n minus 2, then x minus xn, x minus xn minus 1 plus so on. So f of xn, n minus 1, n minus 2, so on x naught, then x minus xn. So first backward difference can be computed as f of xn, n minus 1. So what is the denominator? So just observe the denominator is the same as we subtract smaller term from the larger one, or we subtract the current previous term from the current term. So if current is xn, then the previous is xn minus 1. So xn minus xn minus 1 is the denominator, and f of xn minus f of xn minus 1 is the numerator for first backward difference. It can be written as because the difference between two consecutive nodes is h. So this can be written as f of xn minus f of xn minus 1, okay, divided by h is equal to 1 over h nabla f of xn. So second backward difference, so here should be the backward difference, is defined as, so for the second backward difference we need 3 points, xn, xn minus 1, xn minus 2, and this should be equal to 1 over 2h nabla f of xn minus 1 minus nabla f of xn over h, and can be written as 1 over 2h square nabla square f of xn. And then in general, we can generalize it in the form that f of xn, xn minus 1, xn minus 2, xn minus 3, so on, xn minus k is equal to 1 over k factorial and h power k nabla k f of xn. Introducing backward differences, so polynomial can be expressed as given below. Pn of x is equal to f of xn plus nabla f of xn over h x minus xn plus nabla square f of xn over 2 factorial h square x minus xn into x minus xn minus 1 plus nabla cube f of xn over 3 factorial h cube x minus xn x minus xn minus 1 into x minus xn minus 2 plus so on plus nabla n f of xn over n factorial h n into x minus xn x minus xn minus 1 so on x minus x1. This polynomial, that is 5.27, is called Newton's backward difference interpolating polynomial, so which can be written in a simplified form when nodes are arranged consecutively with equal spacing. So we can suppose that the difference between two consecutive nodes, that is the points of the domain, or the values of x, are equally spaced. So then this polynomial can be simplified in a very good form. Assume that for any real number r, so x minus xn over h is equal to r, so that x minus xn is equal to rh, that is the multiple of h. So then two conjective points xn minus xn minus 1 can be written as, so x minus rh, like here. So if you transfer this xn on right hand side, you will have this xn is equal to x minus rh, this one. So xn can be replaced with x minus rh and minus xn minus 1. So then if the difference between two consecutive values is equal to h, then x minus rh minus x minus xn minus 1 should also be equal to h. So then here you just transfer this RH on the right hand side and you will have H plus RH, and then you can take common H and you will have R plus 1 into H. So X minus Xn minus 1 is equal to R plus 1 into H. Okay, so then similarly for the next two consecutive points Xn minus 1 minus Xn minus 2, so you can have this xn minus h minus xn minus 2 equal to h, that is x minus xn minus 2 is equal to r plus 2 into h. And similarly for the next two consecutive points xn minus 2 minus xn minus 3 is equal to xn minus 1 minus h minus xn minus 3 is equal to h. So this x minus xn minus 3 can be written as r plus 3 into h. So using these values, this polynomial 5.27 can be written as, because now you can replace this x minus xn, okay, with rh and x minus xn minus 1 with r plus 1 into h, and x minus xn minus 2 with r plus 2 into h. So you can replace these terms, okay. Pn of x is equal to f of xn plus r. Nabla f of xn plus r into r plus 1 nabla square f of xn over 2 factorial plus r into r plus 1 into r plus 2 nabla cube f of xn over 3 factorial plus so on, plus r into r plus 1 r plus 2 so on r plus n minus 1 into nabla n f of xn over n factorial using binomial coefficient. So this binomial coefficient minus rk can be written as minus r into minus r minus 1 minus r minus 2 so on minus r minus k plus 1. So minus 1 power k r into r plus 1 r plus 2 so on r plus k minus 1 over k factorial. Okay, so then this Pn of x is equal to f of xn plus minus 1 into minus r1 nabla f of xn plus minus 1 square minus r2 nabla square f of xn plus minus 1 cube minus r3 nabla cube f of xn plus so on nabla n f of xn. So polynomial this 5.29 can be written as Pn of x is equal to f of xn plus summation k equal to 1 to n minus 1 for k minus r k nabla k f of xn. Okay, so this polynomial is actually the Newton's backward difference polynomial, or Newton's divided difference polynomial in the form of backward difference polynomial. Now we can apply on this example. So what is the example is that for the following table of values, estimate f of 7.5. So x values of x is 1, 2, 3, 4, 5, 6, 7, 8. And values of y is equal to f of x 1, 8, 27, 64 and so on. Value to be interpolated is at the end of the table. Thus, it is appropriate to use Newton's backward interpolating formula. So let us first construct the backward difference table for the given data. So 1, 2, 3, 4, 5, 6, 7, 8. And what should be the zeroth difference? So zeroth backward difference should be the exact values, that is 1, 8, 27. So just look in at the second column. So these are exact values of f of x, that is value of the function at point x is equal to 1, 2, 3, 4, 5, 6, 7. Now what's the difference between these two consecutive points is 8 minus 7, 1, 7 minus 6, 1. Okay. Now how we can compute this? Uh, how we can compute this first divided difference? Just subtract 343 from 512 and you will have 169. So since the, the divided This denominator is 1, so if we even divide with 1, so it has no effect. And 343 minus 216, yeah, we will have this 127. Then 216 minus 125, we will have this 91. 125 minus 64, we will have 61. 64 minus 27, we will have 37. 27 minus 8, we have 19. And 8 minus 1, we have 7. Okay, so similarly, thus for the second backward difference, we need to subtract this 127 from 169. So 169 minus 127, we have 42. 127 minus 91, we have 36. 91 minus 61, we have 30. 61 minus 37, we have 24. 37 minus 19, we have 18. And 19 minus 7, we have 12. So then for this third divided difference, backward divided difference, you need to subtract this 42 minus 36, 6. 36 minus 36, 30 minus 24, 6. 24 minus 18, 6. 18 minus 12, 6. And then for the fourth divided difference, backward divided difference, we have 6 minus 6 equals 0. 6 minus 6 equals 0. And 6 minus 6 equals 0. So then we don't need to construct this next differences. So then since the fourth and higher order differences are 0, the required Newton's backward interpolation formula is yx is, it should be yn, not yx, or you can write f of x, n, or you can write even pn of x is equal to yn plus or delta yn or delta f of x, and you can write even plus r into r plus 1 over 2 factorial delta 2 yn plus r into r plus 1 r plus 2 over 3 factorial, so delta q yn. And then in this problem, so r can be written as x minus xn over h, 7.5, which was the value to be determined. So 7.5 minus 8.0 over 1, because the value of h is equal to 1 for the two consecutive points in the domain. So we have a 1 equal to minus 0.5. So, and delta yn is equal to 169. These values we have actually obtained from here, 169, 42, 6 and 0. So this is the same 169, 49, 169, 42, 6. And when we substitute this value in the Newton's backward difference polynomial, so we have this value of uh, f of x at 7.5 is 421.875. Similarly, the next example is construct polynomial based on points 0, 1, 1, 3, 2, 7 and 313. So what we need to do, we have two options. So use Newton's forward difference and backward difference. So first column is representing the nodes 0, 1, 2 and 3. So what's the difference between two consecutive points is 1. So we can write h is equal to 1. And the zeroth difference that is the direct values of f of x. So is 1, 3, 7, 13. So 1, 3, 7, 13. And then the first divided difference backward is 13 minus 7, 6. 7 minus 3, 4. 3 minus 1, 2. And the second divided difference 6 minus 4, 2. 4 minus 2, 2. Third divided difference 2 minus 2, 0. So now we can calculate x minus x naught over h is equal to r. So x naught is equal to 0. So here r is equal to x. So then just replace r. So replacing r, you have this f of x naught plus r delta f of x naught plus r into r minus 1 delta square f of x naught over 2 factorial plus r into r minus 1 r minus 2 delta cube f of x naught over 3 factorial. P3 of x is equal to 1 plus 2x plus x into x minus 1 into 2 over 2 factorial plus x into x minus 1 x minus 2 into 0 over 3 factorial is equal to x square plus x plus 1. Similarly, using Newton's backward difference polynomial, note that h is equal to 1. So for any real number r, we can write this x minus x cube over h, that is x minus 3 over 1 equal to x minus 3. And similarly, if we use this backward polynomial, so okay. Similarly, using Newton's backward difference polynomial, we have this x minus 3. So, and substituting this value in Newton's backward difference interpolating polynomial, we have the same polynomial, what we have obtained using the forward difference interpolating polynomial. So, it means there is no change if we use forward difference Newton interpolating polynomial or backward difference Newton interpolating polynomial. So it depends on our convenience. So what is useful for us or which is convenient to use for us. So, so that is the backward differences and backward difference Newton's interpolating polynomial and how it can be constructed and can be used so to solve the problems of interpolation.